So we're going to talk today about some equations to do with our work energy power notions that we've talked about. So here we go. Going to remind you of a couple of things, and then we're going to seemingly wind our way, and it might not make sense at first. It's like, why is he doing that? But just go with me. Hopefully it would all come together in the end, and we'll have a couple of equations that we can do some problem solving with. So the first thing I want to remind you of is our idea of kinetic energy specifically. So we are going to table any discussion of potential energy for a little bit of time in terms of calculations. That's going to come later. But we're going to start out with kinetic energy, which we shorthand as capital K, capital E, right? So there we go. So this is going to be a mathematical description of the state of an object or system that describes the capacity of that object in that state to affect the environment due to its motion. Okay, and so because it's moving, if it were to interact with something, it would be able to affect it. And we're going to put a number to that. The bigger that number is, the bigger of an effect it can have. That's the general gist of what kinetic energy is about. Now, the other thing we want to really remember is kinetic energy, like all energies, has to be a scalar quantity. It doesn't matter what direction the object is going. Simply, the very fact that it's moving means it has the capacity to affect something. Now, you might not care about it, but as we said in class, one might care about it because it is moving. So that's the first thing that I wanted to remind you of. The second thing is the notion of work. And so we came up with as a definition for work, and I'm going to expand upon this today, is a change in energy. Right? So that's all it is. When work is done, and we're going to use that verb to do with work. So when work is done, the energy of a system or object changes, right? So work is the action that causes the state of the system to change. And the specific way it's changing is it's changing its energy state, right? There's lots of different ways objects can change or systems can change, but here we're talking specifically about a change in energy. Now, I'm going to expand this notion a little bit more now. First, if it's about change, if work is about change, what we know to be true from everything we've talked about so far is that the agent of change is force. Without force, you can't have change, right? So let's expand this notion. And I'm going to have another definition of work that's going to use that. That doesn't replace our definition of work as being a change in energy. It's just an alternate definition that describes how work is done rather than what happens when work is done, right? Because when work is done, the energy of a system changes. How does that happen? So work is the action, or we'll call it the effect of a force that can cause the change in the energy, or a change, let's say a change in the energy of an object or system, right? Okay, cool. So that's that. Not really all that much different, but it brings in this idea of the effect of a force now. So there's a couple of implications of that phrasing. The first implication is that we need force to do work. Okay. The second thing, hopefully, that you get from this is not all forces do work. And where's that coming from? Well, there it is, that can cause, right? And the third thing, this is going to be a little bit more subtle, and we'll get to this, an individual force can do work without a net change in the energy of the system. Okay? Right? So once again, that comes from the word can. And we're going to work our way through this. Sorry for all the terrible puns that you're going to have, but there are going to be a lot of puns. So that's the basis. This is kind of right from our conversation from before. But moving on from there, here's where I'm going to take what seems like it's going to be a sidestep, but really it is directly in line with what we want to talk about. So let's say I have an object moving along a flat plane. We're going to have this be nice and simple to start, right? And so let's say our object is moving to the right along a flat plane, okay? And so the initial velocity is to the right. And if I draw a free body diagram for that, let's say that I have, a normal force acting, I have the force of gravity acting, and let's say I have an applied force acting, okay? So that sometime later then, that I have the object has changed its velocity due to the action of this force, right? Now, in terms of what we just talked about, we're going to say that work is going to get done here because there's going to be an increase in capacity of this object to affect the environment due to the action of this force, because we know here that if this force is in this direction, and that's going to be the net force in the x direction because there's no other forces acting in the x direction. That means that this system is going to accelerate to the right. If it accelerates to the right while simultaneously moving to the right, we know that its speed increases very specifically, right? So it's just like get a couple of those notions together. We know the speed is increasing here because the acceleration is in the same direction as the velocity vector. Remember, this is the symbol for parallel, in the same direction as, right? So that's a speed up. The acceleration, if it is anti-parallel to the velocity vector, we know that that object slows down. And just to remind you, if the acceleration is perpendicular to the velocities we saw in our circular motion unit, this object changes direction, meaning it starts traveling in a circular pattern. Now, that's not going to happen here. I have a flat plane, and we're not doing anything too wacky yet, but hold on to that. All right, cool. So if I use Newton's second law here, I would have F net x equals max. Now, I could put in Fa as that net force here. I'm not going to do that for various reasons that will become clear a little bit later. Here's where we're going to take the side step. Acceleration in the x direction, we know this thing is increasing in velocity. So what I want to do here is I want to substitute for acceleration another equation. And I'm going to go back to kinematics. Now, I know that what I'm going to do is, because I'm using kinematics, therefore, is only true if the acceleration is constant. I will tell you that I can do all of these derivations for non-constant accelerations and come up with the same results if I know calculus. I'm just going to make that claim. If you take the AT class next year, you will see that claim bear out. All right. So there's two things I could put in for this. I know that that acceleration in the x direction is equal to the final velocity minus the initial velocity over time, right? That is a substitution that I can put in here. But also from the equation, Vf squared is equal to Vi squared plus 2a delta s, which in this case would be a delta x, but I'm going to leave it as a generic delta s here. Then I can solve this for the acceleration, and then that's going to be Vf squared minus Vi squared over 2 times the displacement, okay? So I have these two possible substitutions for force. So what do I care about here? Well, actually, if I look at the first one, just something we didn't say in the last unit, but ready? Remember that that time here on the bottom, technically it's a delta time, right? It's the amount of time over which this change in velocity happens. If I substitute this back in here, F net x equals m, well, what's that? Vf minus Vi, well, that's delta V, right, over delta T. So we manipulate that. We get F net X times delta T is equal to M delta V. Well, M delta V, that's a very interesting phrase. Oh, I know what that is. That is the change in momentum of an object as long as the mass is constant. Oh, what's that? Well, that's the impulse momentum theorem. That's the last unit, right? So really, the impulse momentum theorem talks about how the momentum changes as time goes on due to the action of this net external force. So we've already done that. So this is not the substitution that I want to do at this point, because I've already described how forces cause changes to the system over time. When force acts over time, we talk about the momentum changing, right? That's what the impulse momentum theorem says, right? When forces act through time, we're talking about change in momentum. That's what it's descriptive of. Okay? So let's go and look at that other substitution then. So the other substitution then allows us to go F net X equals M, and then I'm going to put in that substitution Vf squared minus Vi squared all over 2 delta S. Boom. Well, that's sort of a mess. Let's, I don't know, let's distribute here. Let's see. You know what? I'm going to multiply both sides by delta S. Why? I don't know, because I know what the result I'm going for is. And so I get F net X delta S, right? Let's actually get rid of F net X. We'll just say F net. F net delta S is equal to, so that goes away, 1/2 mvf squared minus 1/2 mvi squared, right? So that's what I have there. All right, so let's look and see what we have here. So that's interesting. I have these two terms here that are identical. One is the term before the interaction. The other is determined after the interaction. But let's just look at what the term itself seems to say. I have 1/2 mv squared. Now, if I think about that, mass is a scalar, right? Now, I know velocity is a vector, but I'm squaring that thing here, right? So like if I had positives or negatives, that sign would go away. So any indication of the direction is sort of obliterated by that squaring process that we just did here. That means that this term here is a scalar quantity. And it's a scalar quantity then that describes something about a moving object. The more massive that an object is that's moving, the bigger this number is. The faster it's going, the bigger this number is. So it's almost like a number that we can put to something that describes, like, you know, something about its motion. Oh, folks, we're just going to call this or define this as the equation for kinetic energy. And by the way, 3 equal signs is defined as, right? So this term popped out from the math. And what I'm doing now is I'm claiming that and saying, hey, it's a scalar. And it's a scalar that tells me something about how big of an effect that would have if it were to interact with something, right? Because I think we'd all agree the more massive objects, if they interacted with us and they're moving, would affect me more, and that the faster they're going would affect me more. That's everything we said we needed from this concept right here. So since this math seems to fit the description of what we need, right, of coming up with a number that describes the effect something can have when it's moving, why don't we just call it kinetic energy? Right? So Ke is going to be 1/2 mv squared, right? Where v, once again, is not the velocity, it's the speed. The direction doesn't matter because of that squaring. Awesome. So then coming back up to this expression, F net delta S is equal to kinetic energy finally after the interaction minus kinetic energy initially. Well, that's delightful. So what's happening over on the right side of that equation then? Well, this says, if there is a net force that acts over a displacement, this is the change in the kinetic energy that comes out because of that displacement. Yes? Awesome. But there's a problem here. And the problem here is we just defined this is a scalar and this is a scalar, but what we have over here is like two vectors. Force is a vector, therefore net force is a vector, and displacement is a vector. And so I have a vector times a vector yielding this scalar minus a scalar. Now, I can actually collapse the right side of this equation to be delta Ke, right? And so that's just a little bit neater looking. And now, hopefully you see that this mirrors the impulse momentum theorem, right? Except on the right, instead of having delta P, I now have delta Ke. And on the left, instead of having delta T, I have delta S. So whatever this is, and we're going to give a name to it, we're going to reformat the left side in a couple minutes. This is about how forces change energy states over not time or not through time, but over space. Okay? All right, cool. So with that being said now, what we need to do is put it all together. And the way we're going to put it all together is to go back to our notion of work, right? Because I'm going to tell you that that left side of that equation is going to be related to the notion of work. So work is the effect of a force that can cause a change in the object's energy or the state of the energy of the object or system, right? So what do we have here then? Well, that left side is looking pretty good here. It's kind of snazzy because it shows a force doing something, right? So the equation for work should have force built into it, yes? So that kind of makes sense, all right? So our equation for work, which remember has to be a scalar, has to have force built into it. Now notice here, I'm not saying net force, I'm just saying force, because our notion of work talks about the effect of a force, not the effect of net force, right? So individual forces can do individual amounts of work. All right, cool. So work is about a change in energy. So just because I have a force, I don't have a change in energy. For example, I'm holding this pencil up, right? Or this pen up. The state of this pen right now is not changing, even though there's force acting on it. So just because there's force acting on something doesn't mean that change occurs, right? So looking down maybe at, I don't know, my iPod case here, right? There's forces acting. There's a normal force up and there's the gravity force down. No change is happening, right? I think the easiest change to see is if I push this to the side here, the action of my force actually causes the object to speed up. And because we just said that kinetic energy is 1/2 mv squared, when I know when an object is speeding up, that means that there is a change in energy. So evidence that an object is changing in energy could be that the speed is changing. Awesome. But really, if the speed is changing, that means that this object has to change position, right? There's no world in which I push on this and it doesn't move that I can say that work is done. Meaning, I know this seems a little bit convoluted maybe, that the best evidence that change happened is that the object changed position. Because, like for example, if I lift this object, yes, technically I change its speed as I'm lifting it, right? I speed it up and then I slow it down to stop it, right? But here, I think we would all agree that this object gained potential energy. It is more of an ability to affect the environment because of its change in position. So once again, here, a change in position is sufficient evidence to say that work could have been done. So I'm going to put in that displacement figure that we saw before. So what I'm doing here is I'm taking this thing on the left. You notice I'm not using net force yet. I'm just using any old force. But once again, we had that problem of work is a scalar and these are vectors. Well, there's a simple way to solve this. Yes? We can just throw some magnitude signs around this. And so now I've seen to have everything I need, right? So work is equal to force times displacement, right? So in other words, force is needed to cause change, and here's my evidence of change. Boom, we're good because now it's all scalars as well, right? We're good, right? No, we're not. Because watch this, folks. As I push this along, there are actually three forces that are acting, right? So we have actually four, if we want to think about it. We have my applied force, we have the normal force, we have the force of gravity, we actually have the force of friction. So if I think about that, so here we go. So let's draw in those: normal force, applied force, force applied, and then the kinetic friction force. And then this object is displacing over to the side here. So let's say that my forces act over this displacement, right? As this thing is moving to the right, is the force of gravity acting in any way, shape, or form to change the energy of the system? The answer is no, right? Like that doesn't make any sense. Gravity, when I'm moving along a flat plane, is neither causing it to speed up nor slow down, or like there's no change in the state of the system because of the action of gravity when I'm moving flat. Now, if I'm moving vertically, the force of gravity has a major impact, right? Boom, gravity is what's speeding it up. So sometimes gravity causes change, but sometimes it doesn't. Here it doesn't. Same thing with the normal force. The normal force, as this object is moving to the right, is not causing any sort of change in the state of the energy of the system. I think it would make sense that the action, so ready, Fg, this is not going to cause a change in energy. And by the way, why don't we just talk about not cause a change in kinetic energy for now, right? Fn is not causing a change in kinetic energy. I'll just go kinetic energy, right? Right. So if it were the only force acting, it wouldn't be causing a change in kinetic energy. I think we would agree the applied force would attempt to speed up the object, right? Why do I say would attempt? Well, I'm just saying if the applied force was the only force acting, it would speed up because of that, right? The kinetic friction here would attempt to slow down the object. Yes? Not that it is, because if the applied force is bigger than the kinetic friction, this object would speed up, right? But in and of itself, what is Fk doing here? It is trying to slow down the object, right? So different forces are doing different things. So what we need to do is encode that here in our work equation. Because remember what we have so far. We have that the net force times displacement is equal to the change in kinetic energy. And the project or the mental project we're doing here is saying, if this were the only force acting, Fa, right, then that would be the applied force. We know that the applied force would cause a positive change in kinetic energy because the final kinetic energy would be bigger than the initial kinetic energy because it speeds up. So I would want the work of the applied force to end up being positive then, so that this delta Ke is positive. I would want from the kinetic friction, if the kinetic friction were the only force acting, it was the net force, let's say it's already moving, the final kinetic energy would be less than the initial kinetic energy, meaning that I would want this delta Ke to come out negative. So this same product would come out negative. But how could I have two scalars multiplied together and come out negative? That's bizarre, right? The next thing is the normal force. Well, even as this is moving over to the side, the normal force is not causing any change. So I would need a number times a number to end up being zero. Well, and same thing with the force of gravity. So in other words, there must be a third thing in this equation that goes here. And that thing needs to, when I use the applied force, end up with a positive result. When I use the kinetic friction, in this case, it ends up with a negative result. And when I have this, it ends up as zero. So what are we going to do here? Well, hopefully you start seeing that we're going to need to talk something about the relationship between the displacement vector and these vectors. Notice here, the displacement vector is parallel to the applied force vector. The displacement vector is anti-parallel to the kinetic friction. The displacement vector is perpendicular to the gravity force, and the displacement vector is perpendicular to the normal force, right? So if I talk about then an angle, which I will define as theta, and I'm going to define theta in this context to be the angle between F and delta S when drawn concurrently, meaning starting from the same point, kind of like I'm doing here. I just kind of move these off to the side a little bit. What do you notice? Well, here that angle is 90. Here's the angle is 90. Here that angle is 0. Here this angle is 180. And theta in this case has a domain of 0 to 180 degrees inclusive. So there's a domain restriction there. It doesn't make sense to talk about a 270-degree angle here, right? That's just a 90-degree angle the other way. What would do this for us? What would, when theta is equal to 0, give us a positive number? When theta is equal to 180 would give us a negative number. When theta is equal to 90 would give us 0. And hopefully what you figured out is that that is the cosine function. And that is going to be our equation for work. The work done by an individual force is equal to that force times the displacement the object undergoes times the cosine of the angle between that force and that displacement. So there you go. The last thing we have here is I want to go back to this. Notice on this side, I don't have just any old force here, right? Because that's the net force. But notice here, what's going to end up happening is that here, this applied force is going to end up doing positive work, right? Because it's attempting to speed the object up. This kinetic friction is going to end up doing negative work because we're going to plug in cosine 180, I get a negative number, right? And so these are going to end up being 0. The net work, that's going to be the new term, can be found by finding the works of of all the individual forces and then just adding them up, because work is a scalar. I don't care about the direction of the forces anymore because I've taken the directionality of the forces and I've turned it into a scalar using this concept. So then to finish off, here on the left side, this is going to become net work. And I don't need to find the net force anymore to find the net work, because net work is just going to be simply equal to the sum, fancy symbol for sum, of all the individual works done by all the forces, right? So this, folks, is something that's known as the work energy theorem, which should make sense since before our corollary, where delta P was equal to F net delta T, was the impulse momentum theorem. So work energy theorem, impulse momentum theorem, okay? The last thing I want to leave you with is just the following. If work is positive, if work is 0, and if work is negative. So what does it mean for the work to be positive, negative, and 0? Well, if work is positive, that means that delta KE is also positive. That means this object is speeding up or speeds up, right? So here's the thing. If net work is positive, the object speeds up. But if the work done by an individual force is positive, this is trying to attempt to speed up the object. So here, if work is negative, that means delta KE is negative. And that means slow down. That means that the action of this force is attempting to slow it down. If the net work is less than 0, it's negative, that this object actually does slow down. If work is equal to 0, that means that delta KE is equal to 0. That means no change in speed, right? So either that force is not attempting to change the speed of the object because that's perpendicular to the velocity, or the network is 0, in which case there is no change in speed. So there you go. Those are the calculation things that we're going to use this week in order to do some work and energy problems.